Now, next speaker is our distinguished colleague, leader of the program of applied system analysis, academician Professor Arkady Kryazhimskiy. He has been with us for last more than 15 years, leading a very important program. He is going to give our expose of how we think currently about system analysis at IIASA. Arkady.
Thank you, Pavel. In this talk, I'd like to show you a few examples of IIASA's work on systems analysis from a methodological perspective. Here is a symbolic image of a trajectory of a well-understood system. And mechanical systems are good examples of well-understood systems. Mechanical systems may have large dimensions, but a mechanical system is always described by the single mathematical model that predicts its behavior precisely. Systems analysis deals with models of different kind, complex, with systems of different kinds, complex, uncertain systems, usually socio-environmental systems. And here is a symbolic image of a trajectory of a complex system. We have a vague understanding of its structure, elements, and feedbacks, and nevertheless we're in a position to say something meaningful about that system and even characterize its future development. To do so, we have no other way than putting pieces of our knowledge about that system into a model. Inevitably, the model predicts the behavior of the system in some not in all detail, just partially. And for example, if the model is designed by experts in the economics, that model may neglect some important feedbacks from other components of the model, for example, ecological ones. And that may lead to essential failures in the model-based analysis. A way to compensate for such failures is to introduce an alternative model for the system that views the system from another angle, for example, an ecological model. And if we have two models and two outcomes from two models, we can compare these outcomes and understand if the models are structurally compatible, structurally consistent. If they are, we get some evidence for conjecturing that our model-based analysis is not misleading. In other words, we arrive at an important phenomenon, a model cross-verification phenomenon in systems analysis. A natural extension will be to introduce just a family of models that view the system from different perspectives and complement each other in focal points, in complexity, and in scale. And the challenge in this context is to develop a multi-model approach, a set of methods for generating integrated knowledge about the system on the basis of the use of partial models. Certainly we should realize in the very beginning that the multi-model approach can also fail to capture some important phenomena occurring in complex dynamics. Anyway, what a family of models may look like. A family of models could be organized as an hierarchy of models in which complex models are complemented by simpler ones. An example of a successful use of an hierarchy of model is a study that was carried out by IIASA's population group. This study is based on the model that focuses on interactions between changes in population size and structure, agricultural production, resource degradation, and food insecurity and food security. And the complex model that was in the basis of that study was complemented deliberately by a simplified model. And the two models were used in a case study in the Mali case study in Africa. And here on the left figure we see the simulation time series on food secure and food insecure population groups in Mali in the period from 1995 to 2030 for the two models. And on the right figure we see the simulated time series for the resource stock in the country for that same period for the two models. The simple model here does not take into account a population structure in the structure of the population and education, sex, and age. And therefore we see, nevertheless, we see quite good fits in all three dimensions. And these good fits confirmed also in a series of additional original runs allowed the researchers to claim that the education, sex, and age structures in the population have a very small impact on the development of the food secure and food insecure population groups in the country and on the development of the resource stock in the country. And that is an example of an integrated knowledge that is based on the analysis of an hierarchy of models. Family of models could also be organized as could be also composed of models of a same degree of complexity and which that view the system from different perspectives. An example of the use of that sort of a family of models is a recent study that was carried out by the IIASA transition to a new technologies group. The study was focused on modeling the evolution of the global energy system, and the basic model that was used in that study regards the emergence of new technologies as a random process that reflects unpredictability of technological innovation. So here I have shown one of the random runs of the model. Here the ellipses show the technologies that form technological change, and the red ellipses show widely used technologies. The yellow ones show rarely used technologies. Altogether, about 200 runs were simulated, and the researchers analyzed all these individual trajectories, and each individual trajectory acts as an alternative model for the historical development of the global energy system. And the analysis led the researchers to some global conclusions. In particular, the researchers found that the simulated evolution exhibits a period, survives a period of growth and complexity in terms of the length of the technological chains, complexity peak and then decline in complexity. Another finding is that there is a strong tendency to decarbonization, the decline in the carbon intensity of the global energy system. So these conclusions integrate pieces of knowledge which were provided by alternative individual models and thus reveal hidden generic features of the entire system. At this point, I'd like to switch to another challenge in systems analysis that we came across in our studies at IIASA. That's a trade-off between precision and tractability. So a simple illustration. So this curve is intended to represent some empirical observed function, a dependence of one variable on another one. And our goal is to characterize that function in some meaningful terms to reveal its structure. However, as we look at this function, we don't see any regularity here. Here, we can only say that this is a monotonically increasing function, no more. If we put the curve on the grid, we don't see any regularity here as well. However, if we decrease the precision of the grid image of the curve, we arrive at another image, but this image is not regular as well. However, if we triple the size step of the grid in the vertical direction, we immediately arrive at an understanding that the curve is organized as a regular ladder. This is a meaningful statement, but this meaningful statement is expressed in terms of an imprecise image of the object under consideration. An example of the use of imprecise images is a recent study that was carried out jointly by the IIASA Advanced Systems Analysis Group and Evolution and Ecology Group. The study was devoted to analysis of financial data. So this data shows the time series for the Dow Jones Industrial Average and Federal Reserve interest rate for the period between February 2001 and February 2009. In October 2008, the global financial crisis occurred, and the goal of our study was quite modest in this context. We just wanted to understand whether we could see any signals on the upcoming crisis using that limited data that we have on the screen here. And the blurring information, the use of imprecise images of the data that we have here helped us do so. What did we do? We just encoded short windows on the data series in a binary way, by pluses telling us that there is no tendency to a crisis in this window, and by minuses telling us the opposite. And then we use these binary codes to train some stochastic pattern recognition algorithm. And then we used that algorithm to process the data we had. And here is a symbolic illustration for the result. It's a matrix. And each cell of the matrix, its horizontal projection is the target month, the month at which the probability of the crisis to occur is estimated. And its vertical projection is the observation month, the month at which the probability is estimated. And the color of the cell shows the size of the estimated probability. The blue color shows a low probability, the red color shows a high probability, and there is a scale between those two extremes. So that's a result. And we see that, that the application of this blurring methodology to the real crisis actually led us to some meaningful conclusions. In particular, we can see that indeed the probability of the crisis to occur in October 2008 grows over time as the observation month approaches the target month from the past. And the growth rate is quite high. So at this point I'd like to conclude. So in my short talk I tried to show a few examples in order to illustrate two phenomena, two challenges in systems analysis that we came across in our work at IIASA. One challenge is development of a multi-model approach in the application to complex uncertain models, and another challenge is analysis of trade-off between precision and tractability. And these challenges, as well as a number of other ones that we came across in our research, could be analyzed further on at IIASA, in particular within the framework of the Advanced Systems Analysis Forum that has been fixed in the IIASA research plan. I'm deeply acknowledged to a group of my colleagues who contributed to this talk in various aspects, and I'm thanking you for your attention. Thank you.